Okay, so here we have the second part of these extra problem solvings for Unit 3. The first one, a small lump of ice, a hailstone at 0 degrees falls to the Earth's surface. When the hailstone hits the surface, all of the kinetic energy of the hailstone is transferred into thermal energy in ice. Calculate the minimum speed of the hailstone so that it just melts when it hits the surface. The specific heat of fusion of ice is 340 kilojoules per kilogram. Okay, so we've got our formula that Q is equal to mL. That is the heat required to change the phase per unit mass is the L. And now we're saying that Q, that heat, comes from the kinetic energy of the hailstone. So when we have a look at that, conveniently, and this quite often happens, is that your m's cancel. So you're going to get v squared is going to equal to 2l, and therefore v is equal to the square root of 2l. And if we work that out, we're going to have 2. Now we've got times 340 kilojoules. Don't forget this kilojoules, that's times 10 to the 3. And we take the square root of that, we put that into our calculators and take the square root of that, and we should get something like 820 meters per second. So this quite often happens, that the mass is cancelled. So when you immediately look at this and say, oh, I can't do this, there's no mass given, the mass actually cancels out, and so you can do it. By reference to the B question, by reference to your answer in A, suggests where the hailstones are likely to melt on hitting the Earth's surface. Now, it's unlikely because this 820 meters per second is very fast. I mean, if you convert that to kilometers per hour, that's 820 times 3.6. So you're looking at in excess of coming around 3,000 kilometers per hour. So that's very big. It's very likely that the hailstone is going to be reached its terminal velocity a long time before that, or at a much lower velocity. So due to it being so high, due to this velocity being required to be so high, it will not melt. Okay, going on to question 2 here. Says this is a question about thermal physics. Can just about reach there. Okay, so explain why when a liquid evaporates, the liquid cools unless thermal energy is supplied to it. Now we've got 3 marks here, so it's really important when you're doing this that you give all the information. So in evaporation, you have your the molecules with the greatest kinetic energy, EK, will leave. Alright? Therefore, the average or the mean EK of the molecules in the liquid will decrease, because the most energetic ones have left, and therefore the temperature, which is a measure of that mean kinetic energy or the average kinetic energy of the liquid, the temperature will therefore also decrease. Okay. State 2 factors that cause an increase in the rate of evaporation. They're actually 4. There's a larger surface area. We have a higher temperature of the liquid. Temp of liquid. Also, if you get a wind blowing over it, so if there is air movement over the liquid, and also a lower vapor pressure, that will also cause the liquid to evaporate more. Okay, so any one of those, any two of those four. Okay, going on to C. Some data for ice are given below. Actually, let me move this down and have some space to work so that I can do this all. Let's move this down over like that. Okay, so some data for ice and water are given. So we have the specific heat capacity of ice. That's to change 1 kilogram by 1 Kelvin. You're going to need 2.1 times 10 to the 3 joules. Specific heat capacity of water and the latent heat of fusion of ice. So we get given those three. We have 350 grams. Now remember, you're going to need to put that into kilograms. 0.35 kilograms. At 25 degrees Celsius, placed in a refrigerator that extracts thermal energy at a rate of 86 watts or 86 joules per second. Calculate the time required for the water to become -5 degrees. Okay, so let's look at all the energy that needs to be lost by that water. Firstly, we're going to have, as the water cools, from 25 to 0. So there we would have your mass is 0.35 times by your specific heat capacity of water, which is given as 4,200, times the change of temperature, which is going to be 25. That's going to your heat lost for your water as it goes from 25 to 0 degrees. And then the water needs to change into ice, and it's going to give out energy, and that is given by ml. Your formula, the other one obviously was Q is equal to mc change in T. So it's again going to be 0.35, and we're going to times that by the specific latent heat, which is 3.3 times 10 to the 5. And then after it's all frozen, it's now the ice needs to drop a further 5 degrees, so it's going to lose further heat. Still going to be 0.35. The mass will not have changed, but we are going to be timesing it now by the specific heat capacity of ice, because now it's ice, so it's 2.1 times 10 to the 3, or 2,100, and it's going to be 5 degrees. And that's all going to equal to Q. Alright, so that will give us our Q value. Now, once we've got that, this works out to 156,000 joules is equal to Q. Now, power is equal to work over time, or energy over time. So time is equal to work or energy over power. So we're going to get 156,000 divided by your 86, and you get about 1,800 seconds. Everything is given in two significant figures, you see. So your answer must also be in two significant figures. Everything here is in two significant figures. Okay, hope that is clear. Thanks very much.